Hi, welcome to this module on self-testing. Self-testing refers to software systems that can test themselves. Such systems can inspect their own behavior, just as this lemur is doing. In traditional testing, we have a system and a separate test suite. The test suite exercises the system and observes actual behavior. It contrasts this behavior with the expected behavior, warning us if the two are inconsistent. The test suite itself is redundant. It does not add any behavior to the system. And exactly because it is redundant, we can use it to check consistency between expected and actual behavior. With self-testing, we move a bit of this redundancy into the system itself. We do this by adding self-checks, here highlighted in green. These self-checks do not offer any user-visible functionality. Instead, they can be used by the system to check its own health. Such checks first can play a role during software testing. Your well-designed test suite exercises the system under as many different circumstances as possible. The test suite is amplified by the health checks. They act as an additional oracle, informing the tester whether the system is working as expected. Besides use during testing, health checks can be conducted under normal use. The system is up and running and conducts check at certain program points to ensure it is working well and still meeting its mission. The outcome of such health checks are conducted during normal use are monitored by the operations team. All such checks should pass, but if they fail, the operations team observes this and can act accordingly. The simplest form of self-testing is the assertion, a statement expressing that a certain proposition must be true at a given program point. Many programming languages, Java, but also C, C++, Python, have an explicit statement to check an assertion. Here we see the syntax as used in Java. It consists of the keyword assert, after which you can add a Boolean expression. If the Boolean expression yields true, the assert statement does nothing. If it yields false, an exception is raised, possibly with the message provided. In terms of functionality, this statement does nothing. Its only purpose is to add redundancy for self-checking purposes. As an example, here you can see part of the implementation of a stack. It has a method pop, which removes an element from the stack and returns it. This method can only be invoked if there is at least one element on the stack already. The assert statement at the top of the method body here expresses just that. It indicates that the number of elements should be greater than 0 whenever the pop method is invoked. The assert statement at the bottom indicates something about the effect of the pop method. When the pop is done, the number of elements is one lower than it was before the pop method was called, as stored in the local variable oldCount. At runtime, assertion checking can be enabled or disabled. If it is disabled, all assert statements are effectively removed. This is Java's default behavior, so when using asserts, you should always write them as if they are completely unnecessary. In other words, they should be truly redundant. If assertion checking is enabled, you run your application in a self-aware mode. Your application knows better in what state it is, and it may trigger exceptions in case of unexpected situations. It is then up to you to decide how to handle such exceptions. If you do nothing, the application simply crashes. There may, however, be ways to catch such exceptions, to bring back the system into a consistent state, and to restart from there. Assertions offer redundancy and fault tolerance. An assertion at a particular program point expresses a condition that should always be true whenever that program point is executed. If it yields false, this means you did not understand the code when you wrote it. A critical assumption you made and expressed as an assertion does not hold. You need to go back to the drawing board and redesign your algorithm so that it only builds upon valid assumptions. Or there may be a second option. Perhaps it's not your mistake, but a mistake in the code you depend on, for example in some third-party library. Such code may also fail to deliver what it promised. In such cases, your assertions can help to identify what went wrong. You indicated in an explicit assertion which expectations you had. Then the assertion failed. You can now contact the maintainers of the library and point out that failure, suggesting that they deliver what they promised. Thus, failed assertions do more than spotting incorrect statements. When used properly, they can also be used to expose design problems related to interacting modules. In this module, we will look at self-testing in general and assertions in particular. Self-testing may not be as widely used by software developers as, for example, unit testing with JUnit. In safety and business critical systems, however, it is an indispensable fault tolerance mechanism. Furthermore, in DevOps, development and operations are moving closer and closer. This means developers are more and more aware of monitoring needs, for which self-testing is an important technique. In this module, we will look at various self-testing mechanisms, taking the developer perspective. We will cover the basic assert statement, pre- and post-conditions, structural invariants, design by contract, and the Liskov substitution principle. As we will see, these techniques can help you become better at software design and more effective at software testing.